Let's imagine we have a ball or some object that is falling under the influence of gravity. Let's imagine that it starts at some initial height, h0, h0, and drops down to some, oops, there it goes, drops down to some final height, h. The force acting on the object is, we'll assume the only force acting on the object is the object's weight, mg. So the work done on the object by gravity, F delta r cos theta, will be F mg times the displacement. Now what's the displacement? The displacement is the distance that the object falls. In other words, if it starts off at h0, ends up at h, the displacement is h0 minus h. So delta r is h0 minus h. Cosine, what's the angle between them? The force is the weight, the displacement is down. What's the angle between them? 0. So we have cosine of 0. Multiply this out, we get mg h0 minus mg h. There we go, mg h0 minus mg h. That's if we have an object falling straight down. And I'm afraid I can't demonstrate that now. My ball has gone off somewhere, I don't know where it is. What if the object does not go straight down? What if it's, say, sliding down an incline? What is the work done by gravity in that case? Retrieve my ball. Let's imagine that rather than dropping straight down, our ball, say, rolls down or slides down an incline at some angle theta to the vertical. In this case, how much work does gravity do on the object? Well, remember, again, work, and let's assume that the normal force balances, the normal force is perpendicular to the displacement, so again, that's not going to do any work. So, what is the work done by gravity? We have the work is the force delta r cos theta. The force is the weight, mg, times the displacement. Now, the displacement is this distance here, cos theta, where theta is the angle between the force and the displacement. But what is delta r cos theta? Remember, again, delta r cos theta is the component of the displacement along the force. We can see delta r cos theta, if we decompose delta r, that would be this distance right here. Delta r cos theta. But what is that? What is delta r cos theta? Again, it's just h0 minus h. So we could rewrite this as mg times h0 minus h, which gives us exactly the same thing that we got over here. This is a very, very interesting result. This only depends on the initial height and the final height. It doesn't matter how the object got from one height to the other. This work done by gravity only depends on the initial height and the final height. Or it could be going the other way around. If we throw something upwards, the gravity would still be doing work on it, but let me come back to that in just a second. So it only depends on the initial height and the final height. It doesn't matter how it got there. Could go straight down, could go at an angle, doesn't matter. Doesn't matter what the angle is. All that matters is the initial height and the final height, and the mass and g also. One point, if the object is going downward, force and displacement is in the same direction, or if it's going at an angle, at least the angle is less than 90 degrees, the work done by gravity is positive. For an object going upward, the displacement and the force are in opposite directions. So in this case, the work done by gravity is negative. So gravity can do positive work or negative work. If the object is moving horizontally, how much work does gravity do? 0, because the displacement is perpendicular to the force. So gravity can do, and notice, obviously, if it's moving horizontally, the final height is the same as the initial height, and that would be 0. So that makes sense. If the initial height is larger than the final height, it's going down, and the work done by gravity is positive. If the final height is larger than the initial height, it's going up, and the work done by gravity is negative. That all makes sense. And if the initial height and the final height are the same, it's moving horizontally, and there is no work done by gravity. Very, very good. That makes sense. How does all of this fit into the work-energy theorem? Let's take a look. Let's imagine we have a motion of an object where gravity is the only force doing work on the object. This would be the type of motion we've talked about before, where we've got something just flying through the air, projectile motion. It could be going up, could be going down, whatever the motion is. Gravity is the only force doing work on the object. It could be on an incline as long as there's no friction acting on it, no friction doing work. So if gravity is the only force doing work, then the net work done on the object is the work done by gravity. In other words, the net work is, as we just calculated, mgh naught minus mgh. And we know the net work is equal to the change in the kinetic energy, which is Ke minus Ke naught. I want to mix these terms around a little bit. I want to take this mgh and bring it over here to make this Ke plus mgh. And then I want to take this negative Ke naught and bring it over to this side to make it positive Ke naught plus mgh naught. Notice, again, we've got the same thing on the left side as on the right side, Ke plus mgh, Ke plus mgh, but the right side is evaluated initially, and the left side is evaluated finally. We've got the same terms on the left and the right, but one is evaluated in the initial situation, the other one is evaluated at the final situation, other way around. Final situation, initial situation. What does this mean? What is this telling us? Well, if this quantity, say mgh, if that decreases, in other words, if we go from a larger initial height to a smaller final height, then this term over here is larger than this term. But if the sum has to be the same, if this is larger and this is smaller, this must be smaller and this must be larger. So if this term mgh decreases, the Ke must increase. What does that mean? If the object goes from a higher mgh to a lower mgh, the kinetic energy increases. That makes sense. As an object falls down, what happens? It speeds up. Its kinetic energy goes up. It increases. What if an object goes from lower to a higher point? What happens? It slows down. As mgh increases, Ke decreases. What is this quantity? What is this mgh? That is another very, very important quantity. Mgh is what we call the potential energy. To be more precise, we should refer to it as the gravitational potential energy. There are different kinds of potential energy, but for us right now, the only potential energy for the time being that we'll be talking about is the gravitational potential energy. So I will just refer to it as the potential energy. We will write this as Pe for short. We can then rewrite this equation as Ke plus Pe is equal to Ke naught plus, that would be the initial potential energy, Pe naught. So we can see this a little bit more easily. If the potential energy increases, the kinetic energy decreases. If the potential energy decreases, the kinetic energy increases. So basically we can think of it as the potential energy turning into kinetic energy, or the kinetic energy turning into potential energy. So as the object falls, it has a lot of potential energy, and that potential energy turns into kinetic energy. As the object goes up, the kinetic energy decreases and it turns into potential energy, meaning the object is higher up. So we can think of this then as the sum of these remains constant. The sum we refer to, the kinetic plus the potential, we refer to this as the mechanical energy. Which we write as ME. Not me, just ME, mechanical energy. And what this is telling us is that the final mechanical energy must equal the initial mechanical energy. We will see a number of these types of equations where the final value of something must equal the initial value of something. This is what we call a conservation law. And this is actually the conservation of mechanical energy. I'll come back to that in just a second. But let's keep track of when this actually applies. If gravity is the only force doing work, in other words, as long as an object is moving and gravity is the only force doing work on it, then the mechanical energy is conserved. If there are other forces that are doing work on it, then the mechanical energy will not be conserved. There'll be some other things taking place, and we'll talk about that next time. But just for the moment, we're going to assume that gravity is the only force doing work on it, and so the mechanical energy is conserved. Let me write that down, and we'll take a look at that just before we finish up. There's one thing I forgot to mention, and that's just let's take a quick look at the units of potential energy. The units of potential energy will be, because it's mgh, the units of mass times the units of g times the units of h. The units of mass are kilograms, the units of g, meters per second squared, the units of h, which is just a distance, a height, meters. So what do we get? Kilogram, meter squared, per second squared, and obviously that's a joule, as we might have expected. The units of potential energy are the same as the units of kinetic energy, which are the same as the units of work. Very good. So, to the principle of conservation of mechanical energy. The total mechanical energy, ME, which is the sum of KE plus PE, of an object remains constant. When we say something is conserved, we mean it remains constant. It keeps the same value. The total mechanical energy remains constant, of an object, remains constant as the object moves, provided that the net work done by external non-conservative forces is zero. In other words, the work NC, WNC, the work done by non-conservative forces, is zero. What are external non-conservative forces? Basically, we mean something like there are no pushing forces. If I'm pushing this ball, I am doing work on it. That is a non-conservative force. I'm adding energy into the system, into the ball. I am increasing the potential energy. I might push on it to stop it. If I were to catch this ball, I would have to apply a force in the opposite direction and do negative work. In that case, I would be taking energy out of the system. I would decrease the mechanical energy. Friction is another example of a non-conservative force. If friction is acting on an object and slowing it down, it would be taking energy out of the system, doing negative work. So these external non-conservative forces, we're talking about pushing forces, frictional forces, things like that. As long as there is no work done by any of those forces, there are conservative forces that we'll talk about later on that will conserve the mechanical energy, but they will mean we have to put in a different kind of potential energy. We will have to add in another kind of potential to our total mechanical. But for now, for us, we are basically talking about when gravity is the only force doing work on the object. As long as there's no work done by non-conservative forces, then the total mechanical remains constant. We'll take a look at some examples with some numbers next time. I hope that made sense. I hope that was interesting. I'll see you then.